Good afternoon, everyone. I hope you all have been doing fine during this special period time. And I want to thank the organizers for putting together such a phenomenal program, and I'm very honored to be part of it. So it's almost midnight here in my local time, and I'm not sure how long I can stay sharp. So please bear with me if I start to mumble nonsense. Okay, so this picture here down the right shows the beautiful city of Portland, which is 2 hours south of Seattle by car. And I bet you've heard about Portland recently, probably in pictures like this one on the left. Well, this is unfortunate, but let me assure you, the one on the right side is the norm. Anyways, let's get to business and play a prediction game. So imagine a referee, Mr. Sal, picks a function f and prepares it in a black box. And then the player A can query the black box a bunch of inputs xi and get the corresponding function values f of xi. And then A outputs a pair xy in the end. So we say A wins the game if y equals f of x. Well, I guess you'd immediately realize that this condition alone makes it trivial to win the game because it can just ask f on x and output the response, right? So this is not what prediction is supposed to mean. We need to be able to predict at a fresh input, namely this x should not be any of the queries A asked before. Okay, so if A wins this game, then we say that means A can predict the function value at an unknown input. And if no player A can win the game, then we say this function f is unpredictable. All right, so let's look at a few simple examples. So first, let's consider a constant function. So clearly, after one query, we know it all, right? So next, consider a degree D polynomial. And we know that D plus 1 points would uniquely determine this polynomial by interpolation. Okay, and finally, let's consider a random function. So function sampled uniformly at random from all the functions that have n bit inputs and outputs. And here I can claim that on any fresh input that has not been queried before, it is impossible to predict the function value, better than a random guess. This is because we can think of the random function f as being sampled on the fly. So when a new input comes, we just sample a random output and then update the truth table. Okay, so far so good. Now, a new kind of players comes to the picture. So suppose A runs a quantum computer and can make a query in quantum superposition. And it has the same goal in mind to predict f on a fresh input. However, difficulties arise. So suppose A prepares an equal superposition over all inputs, then it appears that this one query already nudges all inputs. So what should freshness mean here at all? Okay, and also because of the quantum non-cloning theorem, the referee cannot record all the queries. So how can we check whether it outputs something that is fresh? So this will be the central question we will address in this talk. But before getting into it, I want to show you that quantum queries are really powerful. So for instance, we said earlier that a degree D polynomial can be identified with D plus 1 classical queries, right? But in contrast, with quantum queries, we just need half of D. And more surprisingly, let's consider a random periodic function. So let's say we sample a random function f and a random value, a random number p, and then we define f sub p by, on input x, we're going to output f of x mod p. So this will be a random periodic function with period p. So as this picture shows, in each p interval, it's random, and then we repeat the same pattern again and again. So to find out p, classically, we basically need to query all of the p numbers. But in contrast, if we can query p in quantum superposition, then there is a quantum algorithm based on quantum Fourier sampling so that we can find out p in a number of steps polylogarithmic in p. So that's an exponential speedup. All right. And next, I want to talk about, why should we care about unpredictable functions? So imagine you're the little boy here, okay? And suppose your friend intends to send you a message saying, okay, let's go find our friend Liang. However, there's a bad guy, who intercepts the message and sends you, let's go hiking instead. Well, if you recognize these characters, it's not a good idea to follow the bad guy's instructions. So what can we do? Well, we can ask our friend to produce a tag, kind of like a certificate to the message, right? And then we are only going to accept the message if this pair of message and tag, they are consistent. They pass some check, right? To make sure the message has not been modified. So namely, we need the communication to be authenticated. Clearly, this works only if the bad guy cannot produce a new tag just by himself, even if he's seen several valid message and tag pairs over time. So you can see this is exactly what the prediction game captures. And in cryptography, there are two primitives providing authentication, which are message authentication codes and digital signatures. And the distinction is in a message authentication code, the sender and receiver, they share the same key. Whereas in a digital signature, the verification key can be made public. Okay, so now that we are motivated, I will talk about how we actually define quantum unpredictable functions and how to construct them, and then towards the end, some fine prints. Okay, so recall, we want to come up with a prediction game that can offer a sensible notion of freshness. So if we give this classical prediction game a second thought, we can realize the equivalent way to describe it. So instead of producing a fresh input and output pair, we can ask the player A just to output one more valid pair than the number of queries that it makes to the function. So we call this the +1 game. Okay, so the player A will win the game if it spends k queries and outputs k +1 valid input and the corresponding function values. Okay, so let me emphasize that these xi values, they need to be distinct, all of the k +1 xi's. So we can state this more formally. So we say a function f is +1 unpredictable if for any polynomial time algorithm A making k queries, the probability that A wins this +1 game is a negligibly small probability. Okay, so all these variables here are functions of a security parameter. You can just think of them as the length of the output of the function f. So this definition actually coincides with the standard existential unforgeable security for message authentication codes and digital signatures. So what's nice about this way of phrasing the prediction game is that it is immediately compatible with quantum queries. Okay, so you can translate it immediately, almost line by line, right? So the player A now is a quantum machine. It can make k queries in quantum superposition and produces k plus 1 classical input and output pairs, right? So the same condition for winning the game. So it would win if these xi's are distinct and the values, the yi's, are the correct function values on xi's. So this is exactly the approach that Bonnet and Gendre took in 2013. So, and I call this the +1 unpredictability. Okay, so just to reiterate, we call F quantum +1 unpredictable if for any quantum polytime algorithm A making k queries, which can be quantum superposition, the probability of A winning the +1 game is negligibly small. So we're going to call it +1U in short. So keep this in mind. And in the same work, Bonnet and Gendre, they also proved that a random function is indeed unpredictable, as we would expect. And showing this is actually highly non-trivial. They developed a very delicate technique called the rank method. Okay, and more recently, Gendre proposed an elegant technique called, which I refer to as the Fourier oracle method. And I believe you can use this method to give a simpler proof, at least, conceptually simpler. All right, so this all sounds really nice, right? And I wish I can just stop here. But unfortunately, something's missing in the +1 unpredictable notion. So what is it? So let's think about it. So for instance, we as the player, we can imagine, we make queries in a subset of input, right? And let's say the strings that start with 1. And then we predict on the input outside that subset. For example, a string that starts with 0. So in particular, we might not care about producing any surplus, but rather we just want to learn something new that the queries don't entail in any obvious way. So to give you some context, let's imagine, again, this bad guy intercepts all the signatures from your friend on the messages that start with from poo-poo. Suppose that was your friend's name. Okay, and somehow this bad guy manages to produce a signature on a message from teacher Jan. Let's go hike 6 Summit Mountain. Well, the consequence of even just this single signature could be life-threatening. Okay, so notice this is a unique concern in the quantum setting because classically, what you've queried will be your property, and whatever you learn is additional. But a quantum algorithm, it might be that it consumes a bunch of quantum queries in order to extract something new. So in particular, this type of attacks, which we may call, query here, predict there, this type of attacks is not ruled out by the +1 unpredictability definition. So to remedy this, we propose a new notion. It directly addresses the issue we just saw. So let's think of what we call a blind prediction game. So here, the referee will pick a blind set B epsilon just by including each input x with probability epsilon independently. So namely, this blinding set B epsilon will be a random subset of size roughly epsilon fraction of the entire domain. Okay, and then we blind the function f on this set B epsilon, meaning for inputs in this blinding set, we will output a special symbol, an error symbol bottom, and we keep up, outside the blinding set, we keep f as is. Okay, so then we had this blinded function f to the player who plays the same game, like make a bunch of queries, and then produces one output. And this output is supposed to be, so this x here is supposed to be in the blinding set, and y should be the correct function value. So that's how A can win this blind prediction game, to predict a function value for input in a blinding set. Okay, so this gives our formal definition of blind unpredictable functions. So we call f is blind unpredictable if for any quantum polytime algorithm A, it cannot win the blinding prediction game with probability bigger than negligible. Okay, so in fact here, let me remark that this parameter epsilon can be specified by the player A, and it's actually sometimes more convenient in this way. Okay, so the only condition is the blinding set B has to be sampled randomly. So there are other nuances in this definition which I don't want to get into. You can check out our paper. And speaking of, let me acknowledge my co-authors, Gorian Alagic from University of Maryland and Christian Mayens at CWI and Alex Russell at University of Connecticut. Okay. So now we have this new blind unpredictable notion. The question is it a good one? Well, the answer has to be yes. And there are many reasons I want you to believe that is the case, and you will like it. So first of all, we can show very easily that a random function is indeed blind unpredictable. And this is what you would expect from any reasonable unpredictable notion. Okay, and then we show that the blind unpredictability actually subsumes existing unpredictable notions. So that means we take care of this new type of attacks, but in the meantime, we don't lose any security guarantees in the existing notions. So that's always good. And in fact, quantum blind unpredictability is strictly stronger than +1 unpredictability. Okay, we show this by an explicit construction, which is +1 unpredictable, but nonetheless can be broken by exactly this type of attacks which query here and then predict there. So namely, it's not blind unpredictable. So this shows the relations between the existing notions of unpredictability. And let me remark that when we're restricting to classical players only, then both blind unpredictability and +1 unpredictability, they're both equivalent to the standard existential unforgeability. Okay, now let me take some water. So in the rest of this talk, I will show you constructions of blind unpredictable functions and some further characterizations of the new notion. So this will be the evidence that BU is really a right notion. Okay, now for starters, let's prove that a random function is blind unpredictable. So recall in a blind predicting game, the referee samples a blinding set, okay, uniformly at random. So well, actually, we first sample this uniform random function, and then the referee samples the blinding set B, and then we run the player A with the blinding function BF. So actually, we can imagine an equivalent way of setting up the game. So instead, let's first sample the blinding set B epsilon. And then we sample random functions separately on the blinding set and its complement, and we call them R epsilon and R naught respectively. Okay, so notice that R naught and R epsilon combined, they're distributed identically to the uniform random function f. Okay, then running A with the blinded function f is equivalent to running A with R naught only, right? And then the winning condition would become, outputting x in the blinding set such that R epsilon evaluated at x equals y. Okay, now with this, once we have this way of playing the game, we can observe that A only interacts with R naught. In particular, whatever A outputs, it will be independent of R epsilon. Right? So that means the output x and y, they will agree with R epsilon with probability 1/2 to the n, because R epsilon is randomly chosen independently. So that shows a random function is blind unpredictable. Okay, good. Now we know a random function is unpredictable. It is, however, not practical, right? Because if we want to sample a random function, a truly random function, we're going to need exponentially many random coins. So for that reason, people come up with the notion of pseudo-random functions, which would be an efficient approximation to a truly random function. So a pseudo-random function, or PRF in short, is actually a family of functions indexed by this k, okay? And we call this indices a key, if you wish. So it has to satisfy two conditions. One, for each key which determine the function fk, we should be able to compute it efficiently. All right, and then more importantly, this function has to mimic a random function very well. And formally, we would consider a distinguishing game, right? So let's think about the referee who picks a black box function, which is either sampled, uniforms as random, so it's a truly random function, or the referee picks a random key instead, and then picks the corresponding function from the pseudo-random function family. Okay, and then it should be difficult for any player to tell which case it is. So this is what we mean by a pseudo-random function. It's indistinguishable from a truly random function, and it's efficiently computable. So since a pseudo-random function is indistinguishable from a truly random function, as a corollary, we immediately can see that a pseudo-random function is also blind predictable. And in case you wonder, pseudo-random functions can be constructed from standard cryptographic assumptions, and also in practice we use block ciphers such as AES. All right. So far, our examples of unpredictable functions all have a fixed input length. And can we build unpredictable functions with inputs of arbitrary input length? Okay, so this is motivated by cryptographic applications where we want to, for example, sign messages that are arbitrarily long. So in fact, this problem has been studied a lot in the classical literature in various contexts, such as domain extension or modes of operation for block ciphers. And there are lots of schemes that convert a pseudo-random function on fixed inputs to process messages of arbitrary length. Okay, so if these schemes remain quantum secure PRF, then we can get blind unpredictable functions for arbitrarily long messages too. But, well, the reality is that some of the schemes are broken under quantum superposition attacks. But we do have a few quantum secure ones, and this was proven in a prior work of mine. Okay, so as a corollary, we can say that if we have a pseudo-random function f, then we can construct quantum blind unpredictable functions for arbitrary input length. Okay, but one drawback of pseudo-random functions or block ciphers like AES is that they're usually very slow. Okay, and this becomes more and more a problem when we want to process longer and longer messages. So actually, an alternative approach is to first compress your input to a short one by a hash function. Okay, and this is usually called the hash and MAC paradigm. And it's been proven classically that if the hash function is collision resistant, meaning it's difficult to find a pair of inputs x0 and x1 such that they get mapped to the same function value, then if we compose H with the fixed length unpredictable function f, this composition remains unpredictable and we can handle arbitrarily long messages. But unfortunately, this fails against quantum players. So think of H as the random periodic function, as we mentioned in the beginning. The classical algorithm cannot find the collision efficiently, but a quantum algorithm can. Okay. So notice that this doesn't mean that we should just abandon this approach. It just means collision resistance itself is not sufficient. So instead, we would ask, what would be a sufficient property for the hash function for this paradigm to work? Well, it turns out we can define a notion which we call Bernoulli preserving for a hash function. And then we can show that if we compose f with a Bernoulli preserving hash function, it remains unpredictable. So what is Bernoulli preserving? I mean, this name is a little bit weird, but actually, as we can see, it's actually a natural notion. So again, we consider a distinguishing game. So the referee will pick a blinding set in two ways. Okay, either the referee directly samples in the domain, so that's the standard way, or the referee will first pick a blinding set C in the codomain, and then take the inverse H inverse to define the set in the domain. Okay, and then we define this characteristic function on the set B, so which will be 1 on inputs in the set and 0 otherwise. So we call this hash function Bernoulli preserving if no player can tell which case it is. All right, so I'll say more about Bernoulli preserving towards the end if there's time, but let's move on for now. Okay, so as we discussed earlier, unpredictability can be applied to define security notions for authentication. And in particular, all the blind unpredictable functions we've just seen, they readily give quantum blind unpredictable message authentication codes. So as an additional contribution, we show that the famous Lamport one-time signature can be proven quantum blind unpredictable in a random outcome model. Okay, all right. So I guess so far, most stuff is kind of on the conceptual level. Next, we'll get our hands dirty and get to some technical details. But no pressure. There won't be much since my brain would probably explode. Okay, so recall the relations among the unpredictable notions we claimed before. So I like to go through this classical equivalence just as a warm-up. Okay, so I want to show you that +1 unpredictability is equivalent to blind unpredictability when we restrict the players to classical players. I guess I'll leave the implication from +1U to BU as an exercise. Right. So namely, if no player can produce a surplus, then no player can predict in a blinding set. Now let's look at the other direction, that blind unpredictability implies +1 unpredictability. And it's usually easier to prove the contrapositive, namely, assuming there is an adversary, there is a player A, then can win the +1 game. And then we want to show a player A prime, which can win the blind prediction game. And in fact, A prime would be rather straightforward. We just run the player A with the blinded oracle BF, where we pick epsilon to be 1/k. Okay, so A would make k queries and then produce k +1 input and output pairs. And then A prime will just pick one of them at random and output it. So let's see why this A prime wins the blind prediction game. So first, observe that with constant probability, all the k queries from A will be outside the blinding set. Okay? So that would mean that whatever A outputs here, it will behave the same as in the original game. So all these k +1 pairs will be valid. Okay, and then because of the random choice of the blinding set, some of these xi's will be there with probability something like k epsilon. So in overall, A prime will win the blinding prediction game with probability something in the order of epsilon. And we know epsilon is 1/k, which is inverse polynomial, not negligible. So this shows A prime would win the blind prediction game, which is a contradiction. Okay, now getting into the quantum setting, we can still argue that blind unpredictability implies +1 unpredictability. But the classical analysis no longer holds. For instance, we can no longer say that the player A never queries the blinding set when the queries can be quantum superposition, right? So instead, we first prove what we call a simulation lemma, which basically bounds the deviation of A from between running with F and running with the blinded oracle B epsilon f. Okay, so this would imply whatever A outputs in this simulated game is still going to be valid pairs. Okay, and then we just need to show some of these xi's are indeed in the blending set with some noticeable probability. And we show this by extending the Fourier oracle method to non-uniform distributions. All right. So actually, the reverse direction is probably more interesting because it explicitly shows that +1 unpredictability fails to guard against the type of tags which query here and predict there. Okay, so to construct such an example, which is +1 unpredictable, but which is not blind unpredictable, let's first recall some facts. Okay, so we know a random function is unpredictable under both notions. And also we know quantum Fourier sampling can find the period of a random periodic function. So how about the following construction? So I'm gonna partition the domain into two subdomains, strings starting with 1 and strings starting with 0. All right, and then I'm going to pick a random function g and a random period p. And for prefix, for inputs with starting with 1, you know, something like 1x prime, I'm going to output gx prime mod p, meaning on this input, on this one subdomain, it's going to be a periodic function. And then I'm going to pick independently a random function h on the 0 subdomain, except I'm going to puncture at this special point zp. So for zp, I'm just going to output all 0 string. So what does this function give us? Well, I guess it should be clear that it is not blind unpredictable, because we can just query in this subdomain, right, to figure out the period p. And once we know p, we can predict on 0p, which is just the all 0 string. And this is public information. Okay, so this trivially wins the blind prediction game. So this will give us a separation if we can prove this construction is +1 unpredictable. Intuitively, right, since G and H are both random, then they are +1 unpredictable. So it seems that, you know, the only possible surplus has to come from this special point. And that means we would need to find P. Okay. Now, if you have seen the quantum Fourier sampling algorithm, it seems rather destructive. Right? You make a query and then you measure it under the Fourier basis, and you repeat this multiple times. Right? So it appears that once you figure out the period P, all the queries will be kind of collapsed, and you don't learn the values of G. Wait, here we go. But unfortunately, this intuition is not correct. The Fourier sampling actually can be reversed. So we can actually learn a bunch of G of x in addition to the period P. So this counterexample doesn't quite work. But don't worry, okay? the difficulty actually also gives us a way to fix it. So the idea is to enforce the player to make a choice when querying in the one subdomain. So either it will learn the period, okay, and forget about the function values, or it just learns some function values. So to this end, we're going to append another random function, f. Okay, so in particular, to run quantum period finding, we'll have to get rid of f and only keep g. So we're going to lose the information on f. That's good, right? Otherwise, if we keep everything, both g and f, we will learn the function values for g and f, but then we don't find the period. So any player has to solve this dilemma. That means it cannot produce a surplus. Okay, so we can turn this idea to prove formally that this new construction is going to be +1 unpredictable. Oh, I should point out that on the 0 subdomain, it's pretty much the same thing. Okay, we have this special point, which is a trivial output. Otherwise, it's another independent random function. Okay, so this construction is going to be +1 unpredictable. And we can still see that it is blind predictable because we can still find the period. Now it's just every time we need to make 2 queries in order to uncompute f and just keep g and feed that into the quantum Fourier sampling procedure to find the period. Okay, I guess I'm almost, probably already over time. Let me just briefly finish the next couple of slides. So we've been using random functions as a benchmark for predictable for a while. And we've also seen that pseudorandom functions, they give us a very good approximation. And in fact, pseudorandom functions are strictly stronger than the unpredictable notions. You can easily construct a counterexample, which is no longer pseudorandom, but it remains unpredictable. So a natural question, why would we bother with unpredictable notions? Why can't we just always use pseudorandom functions? Well, I guess the answer is mostly concerns from practice, because pseudorandom functions are usually computation. It requires a lot of computation. Okay, and also the hash and mag paradigm, it may not be pseudorandom function in general. And we would hope to construct more efficient schemes satisfying the slightly weaker unpredictable notions. Okay. Well, I guess I'll just skip this slide and let me wrap up. So we've seen the blind unpredictable notion, and the study of it offers further insights for reasoning about quantum security in the presence of quantum superposition attacks. Right? So going beyond, I think this blind unpredictable notion provides a viable way to study more cryptographic primitives. For example, you can ask more constructions of digital signatures satisfy this notion. And we can also study multi-time authentication for quantum states. Okay, and then I just want to point out this new notion of Bernoulli preserving hash. I think it can be useful in other contexts. And it will be interesting to see whether the standard, hash functions like the sponge construction behind the SHA-3 family can satisfy this new notion. Okay, well, before I stop, let me share a recruiting advertisement. I have funds for PhD students and possibly postdocs too. So shoot me an email if you're interested. All right, and thank you, and I'm happy to take any questions.
Thanks, Fang Song, for the really nice talk. I really like the example you use. I mean, the TV show, the Video Corner.
Yeah.
I really like that.
Better be careful.
Okay, let's go back to, I have a few technical questions here. As you already showed that the +1 game cannot imply the BU in the quantum version. I mean,
Yes.
in the quantum setting. So if we make it stronger, I mean, like not +1, but plus like epsilon fraction, will that be, I mean, the two, can we get any?
Okay, very good question. So I guess you're suggesting strengthening on the +1 notion, where instead of producing one additional input and output pair, we ask the player to produce a few more, like 2, 3, or even polynomially more.
Even
I mean,
a fraction,
that's right. I would imagine, this kind of hierarchy of definitions, there might be separations between them, but I don't think this captures the issue that we considered. Like,
okay.
I guess the fundamental challenge here is, it doesn't seem to rule out this type of attack where we query within a subdomain and then predict in somewhere else.
Okay.
So you can imagine when you produce like more and more pairs, it it doesn't violate getting into this different domain.
Okay.
Yeah. Okay. So I would still think they will be separated.
Okay. Yeah. I at least I got the feeling. Okay. So my next question is on the opposite. So in the classical setting, I mean, the +1 is well defined, but if we consider this in the information hierarchical way, like the entropy, so can we define, for example, plus 1/2 or plus 1/3 game?
Okay.
Yeah, in the entropy sense.
I guess, that's a very good point. I guess you could.
Okay.
Right. So you just say, okay, after I interact with the oracle, my uncertainty about the oracle increases by a little bit. I think we can define such a notion, and that's a good direction. I haven't thought about this, and maybe there are existing constructions that already satisfy this information theoretical notion.
Yeah, I think maybe in classical case, at least, I mean, there should be something.
Yeah, I mean, a random function should definitely be a candidate. I think anything reasonable, they should, a random function should satisfy it.
Okay.
Yeah, that's my intuition.
Okay. So my last question, as you mentioned that PRF actually is stronger than all the definitions here. So we know that there's something, I mean, instead of PRF, there's other definitions. So do you think there's also other concept which can imply this BU or?
I see. So you're asking, okay, so we're building this hierarchy now. We have +1 at the bottom, and then BU one step up, and then PRF on the top. So you're asking if there's something between BU and PRF?
Yes. Some natural.
Right. Well, I mean, I guess the short answer is I don't know of any, but I don't think it's impossible to define some notion in between. But then, as your last part specified, if you are looking for some natural notion, I actually couldn't think of something in between, like which would be natural.
Okay.
Because it seems like our blind unpredictability really captures what in terms of learning something new from a function, what is possible and what is not possible. So it seems to be a precise characterization. Yeah.
Okay.
So yeah, I guess right now I couldn't think of any natural notion in between.
Okay. Okay. Thanks.
Possible.
Thanks. Okay. I don't know whether are there any questions from the room? I mean.